Okay, so now we actually start analyzing our recursive functions since we know how they work. So to start with the time complexity, we show what is called a recurrence relation. So the time complexity of a recursive function is also defined using itself. So in here, for our recursive function over here, which is factorial, the time it takes to get the factorial of n minus 1 is the time it takes for us to get the factorial of n minus 1, plus some constant accounting for the multiplication and then the other under the hood stuff that runs in constant time. And then otherwise, when we get the factorial of n equals 1, we just need a certain constant amount of time. So moving on, starting from this recurrence relation, we can sort of simplify we should somehow simplify this to no longer include itself in the definition in order uh, to properly measure the time complexity of our function. So there are several ways to get that. So one particular way is the substitution method, wherein we try and expand our recurrence relation up to a point where we can see a sort of pattern. So in this case, we first expand t of n minus 1, which should be equal to tn minus 2 plus some constant c1. And then if we combine the like terms, we get this expression here. Now, if we expand t of n minus 2, we get t of n minus 3 plus c1. And then when we combine the c1 terms, we get 3c1 over here and a tn minus 3 over here. Now, if you try and expand t of n minus 3, you get ta of n minus 4 plus 4c. And then after another step, we get t of n minus 5 plus 5c. So you can see sort of a pattern here, wherein the coefficient of c1 is exactly equal to the term we subtract n by in the t n minus something part of the recurrence relation. So let's substitute a variable k for those numbers. So we have t of n minus k plus kc1, which will be true for each step here in the expanding process. So you can prove this through induction, but this is left as an exercise for you. So now that we have this, we know that when n equals 1, or the thing inside this call is 1, t of n just simplifies to a constant c2. So if we let k equals to n minus 1, so our term here becomes n minus 1, and k here becomes n minus 1. This term becomes t of 1, which is defined as c2. And then we have an n minus 1 times c1 term over here. So applying the rules for the asymptotic big O notation, we have a couple of constants and a term multiplied by n. So the big O notation, or the big O of our factorial function over here, is linear with respect to the input n. So that's it for the substitution method.